Welcome to NovaSleep, where science slows down and the universe reveals its secrets one breath at a time. Tonight we follow the speed of light, nature's ultimate rhythm, the set law that governs everything that moves, shines, and lives. As you listen, each fact will unfold like a soft pulse in the dark, a reminder that even the fastest thing in existence carries peace within its motion. So settle in, breathe, and let the constant heartbeat of the cosmos lead you into rest. By the way, if you like and subscribe to my video, this is the most effective way to support me. If you can tell me where in the world you're watching from and what time it is, I would love to read it in the comments. 1. The meter is defined by how far light travels in a slice of time. The modern meter is anchored to the vacuum speed of light and to the definition of a second, which is counted by the regular rhythm of a specific atomic transition. By fixing a single exact number for the vacuum speed of light, metrology turned every measurement of length into a measurement of time multiplied by that constant. This removed dependence on metal bars and thermal expansion and gave laboratories across Earth a common ruler that cannot warp with weather or age. Precision that once needed volts and careful guards now lives inside clocks and optical paths. This choice made distance portable. Any laboratory with an accurate atomic clock and a stable laser can create the same meter that any other laboratory can create. The calibration chain collapses to a simple procedure in which one compares a laser frequency to the atomic rhythm, and then counts the time light needs to traverse a chosen path. This broadcasting of standards through physics rather than artifacts eliminated regional biases and errors that once plagued engineering. Drawings and international trade. It also integrated the sciences. Astronomy, geodesy, and semiconductor manufacturing now speak the same language because their rulers are not artifacts but light-based intervals. When engineers etch features measured in nanometers and when navigators triangulate continents with satellite ranging, they are using the same physical anchor. The meter no longer asks for trust in a bar stored in a vault. It asks for trust in a constant property of nature that appears to be identical in every tested direction and location. 2. Light in vacuum fixes the ultimate speed for cause and effect. The vacuum speed of light is not merely a property of illumination. It is the fastest speed at which any influence can travel, which welds together the idea of cause and effect. Events can influence only those regions of space and time that sit inside their future light cone, a geometric boundary traced by the signals that would move exactly at the vacuum speed of light. Anything outside that cone cannot be reached without breaking the structure that keeps effects following causes. This boundary preserves consistency among observers who move relative to one another. Two observers who disagree about the order of events that are widely separated will still agree about which events can be connected by a signal. The impossibility of a faster messenger keeps paradoxes from erupting and prevents contradictions in which an effect appears before its cause in someone else's frame of reference. The same speed that carries sunlight to Earth therefore defends logic itself across the universe. The constant cuts across all known forces. Experiments with high-energy particles, with gravitational waves from colliding neutron stars, and with radio pulses from distant galaxies show that nature uses a single limiting speed for the spread of influence. This unity is why fields that look different on small scales can be described with common mathematical structures. The cosmic speed limit is not a trick of optics, it is the backbone that determines how the information can be sent, received, and preserved. 3. Why clocks slow down as motion nears light speed. A moving clock does not tick at the same rate as a clock at rest relative to the observer. This is not a flaw in clockwork, but a property of space-time revealed by the invariance of the vacuum speed of light. If a light pulse must cross a fixed distance inside the clock, and if the measured speed of that light must remain the same for all observers, then the only consistent solution is that the time between ticks stretches when the clock moves. The geometry forces the dilation. This slowing is not small when speeds become a large fraction of the vacuum speed of light. Particles in accelerators live longer than identical particles at rest because their internal processes are running on dilated time. Precise aircraft and satellite experiments compare atomic clocks and record the discrepancy that motion creates. These effects have to be corrected in navigation systems or position errors would grow rapidly with every passing minute. The theory was once a bold idea. Now it is a practical checklist item in engineering. The result ties motion to time in an inseparable way. A traveller who moves fast ages less between two meetings than a colleague who stays home. The effect is symmetric in pure motion, yet it becomes asymmetric when real trips involve turning around or gravity. What appears as a puzzle at first becomes transparent when one draws worldlines and light cones. The invariant speed sets the rules, and the rules reshape intuition about simultaneity and duration. 4. Time does not pass the same for a photon. A photon moves at the vacuum speed of light and therefore follows a path for which the interval of proper time is 0. In the mathematics of space-time, that means no time elapses along the path of a photon from the emission event to the absorption event. This does not grant the photon a subjective experience. It states that the clock that would ride with a photon would never advance because such a clock cannot be built to move at that speed. This property explains several features at once. The lack of proper time along the path is consistent with the impossibility of a rest frame for light. There is no transformation that brings a light pulse to rest. Any attempt would tear the fabric of the equations that keep the vacuum speed of light invariant. The geometry classifies paths into time-like, light-like, and space-like, and only the first supports clocks that tick between events. The idea changes how one imagines travel across cosmological distances. A photon emitted in the early universe and captured in a radio telescope today has crossed billions of light years in a cosmos that has expanded the space between galaxies. Yet along that path, the proper time remains 0. The contrast between the immense time measured by cosmic calendars and the null time along the photon's world line reveals how space-time keeps its categories strict, even while the universe evolves. 5. The shape of moving objects changes in a way eyes cannot directly see. When an object moves close to the vacuum speed of light, its length along the direction of motion becomes contracted relative to the length measured at rest. This Lorentz contraction is not a squeezing by forces, but a geometric relation between measurements made in different frames. If one tries to photograph such an object, the result is not a simple squashed shape, because light from different parts of the object takes different amounts of time to arrive. The combined effect is known as the Terrell rotation. A fast-moving sphere can appear rotated rather than flattened, because the camera collects light that left different parts of the surface at different times. Edges reveal details that would be hidden if one were only thinking about static shapes. The image is a composite of light travel times and motion. What the eye interprets as a surface is a carefully timed quilt that has been stitched by photons. This teaches that perception at extreme speeds becomes a choreography between emission and arrival. Artists and simulation designers who want to portray relativistic motion must compute not only the contraction, but also the changing directions from which light arrives. Without that correction, the result would mislead. The real picture is both stranger and more coherent. Space and time weave a view that honours the invariant speed, while preserving the consistency of geometry. 6. A mirror can measure the size of the solar system. Astronomers time the travel of laser pulses bounced off retroreflectors placed on the moon and record the round trip down to trillionths of a second. From that tiny time span, one computes distance through the vacuum speed of light. The method extends to radar echoes from planets and to signals that brush past the sun. The solar system becomes a network of mirrors and clocks that reveal its scale without relying on parallax or assumed sizes. This timing enabled a chain of discoveries. Radar ranging to Venus tied the astronomical unit to a direct physical measurement. Lunar laser ranging continues to map the slow recession of the moon as tidal interactions move energy around in the Earth-Moon system. The same technique checks aspects of gravity by comparing how light and matter respond to the sun's pull during the flight. Each measurement is a story in which a pulse leaves, the clock waits, and the universe answers with a return. The approach is robust because the signal needs no calibration as a yardstick. The vacuum speed of light and the counted time define the distance. Even atmospheric effects and instrumental drifts can be modelled and subtracted because they leave signatures in the way the return signal broadens or delays. The mirror becomes a tool for dynamics as well as geometry. Through light and time, the solar system becomes a laboratory with the rulers that never wear out. 7. The sun is already in the past. Sunlight takes little more than 8 minutes to cross the average distance between the sun and Earth. The glow that warms the face and the flares that decorate the limb therefore belong to a past moment when the sun was as it was then. The delay is not an inconvenience, but a window into the past that becomes larger with distance. Every star is a museum display with a label that says the light is a relic of an earlier time. This delay matters when spacecraft navigate and when scientists monitor solar storms. Commands and telemetry must be planned with the knowledge that the electromagnetic messenger carries news no faster than the vacuum speed of light. Instruments that watch the sun and satellites that guard power grids during storms both operate inside a schedule set by nature. Planning becomes a negotiation with delay that never goes away. The idea scales to the cosmos. Galaxies billions of light years away show us structures that have evolved during the travel of their light. The telescope becomes a time machine that cannot be rushed. Light refuses to reveal the present state of distant things. It offers a history book instead. Understanding that gift removes confusion and invites a deep patience with the way information moves through space. 8. Gravity bends light without touching it. When a light ray passes near a massive body, its path curves because the space-time itself is curved. The bending is gentle for planets and stars and fierce near black holes. The angle depends on the mass and on how closely the light grazes the mass. The effect was famously checked by measuring the apparent shift in the position of a star during a solar eclipse when the starlight ran close to the sun on its way to Earth. This bending creates natural lenses. Distant galaxies can be magnified, sheared into arcs, or even multiplied into several images by foreground clusters. Time delays between those images allow measurements of cosmic distances because the light takes longer along paths that skirt deeper wells of space-time. Each lensed system becomes a set of paths with built-in stopwatches. The cosmic speed limit and the shape of gravity together create a surveyor's toolkit on an intergalactic scales. Near a black hole, the deflection becomes dramatic. Light can orbit in a precarious ring at the photon sphere before falling inward or escaping outward. The ring that telescopes have resolved around massive black holes is not a solid surface. It is a crowd of light paths that loop and almost loop compressed into a glowing edge by extreme curvature. No hand touches the beam. Geometry alone bends the route and writes an image. 9. Empty space can slow light when it is not truly empty. The phrase empty space hides a restless structure filled with fields that fluctuate in quantum fashion. In regions with extreme electromagnetic fields, or in carefully arranged boundaries, these fluctuations can alter how light propagates. The effect is minute under ordinary conditions, yet calculations and proposed experiments suggest that vacuum polarization and similar processes can shift the effective refractive properties of space itself. The vacuum then behaves like a material that is almost but not quite empty. Strong magnetic fields near neutron stars provide a possible stage. Photons moving across such regions may experience different indices of refraction depending on their polarization, which can rotate the plane of polarization in ways that astronomers can attempt to detect. The change is not a classic slowing by atoms, it is a modification of propagation by the sea of virtual excitations permitted by quantum rules. The photon meets no atom yet feels a fog. Laboratory ideas explore boundaries made by parallel plates where electromagnetic modes are suppressed. In such a setting, some proposals predict a tiny increase in the maximum signal speed known as the Scharnhorst effect. If present, it would be unimaginably small and wrapped in caveats that keep information from surpassing the vacuum speed limit. The broader message is that empty is a word used for convenience. The deeper the probe goes, the more structure is found hiding in plain space. 10. A particle can outrun light in water and glow blue. In media such as water or glass, light travels slower than it does in vacuum because the electromagnetic wave is repeatedly delayed by interactions with the material. A charged particle that moves through the medium faster than light can move, in that same medium will emit a cone of radiation known as Cherenkov light. The glow is often blue because the effect is stronger at shorter wavelengths, where the medium slows light more. This glow is not a violation of the cosmic speed limit. The particle is still slower than light would be in vacuum. It only outruns the local wavefront inside the material. The geometry mirrors a sonic boom where a plane outruns sound in air. Detectors use this radiation to identify fast particles and to measure their energies and directions. The cone angle records the ratio between the particle speed and the local light speed inside the medium. Gigantic detectors under mountains and inside deep ice watch for faint Cherenkov flashes to catch neutrinos that pass through Earth in countless numbers. Nuclear reactors shine underwater with the same spectral blue because energetic particles pour through the moderator and trigger the effect. The phenomenon turns a passive medium into an active witness that writes a signature whenever something fast passes through. It is another reminder that speed limits live in context rather than in slogans. 11. The first speed of light on Earth was counted with a toothed wheel. In the 19th century, Hippolyte Fizeau interrupted a beam of light with a spinning toothed wheel and measured the speed at which the light vanished and reappeared after reflecting from a distant mirror. By tuning the rotation to the threshold where the returning pulse was blocked by the next tooth, he read a frequency that, combined with the distance, gave a value for the speed of light. The method turned a beam into a stopwatch. This approach avoided astronomical uncertainties. Earlier estimates had used the timing of eclipses of the moons of Jupiter, which rely on orbital models and long lines of sight through atmospheric turbulence. Fizeau's device reduced the universe to a hilltop, a wheel, and a distant mirror. The principle anticipated modern frequency combs and optical clocks where counting replaces continuous measuring. Discrete events are easier to compare precisely than analog sweeps. The experiment also revealed the practical challenges that precision demands. Alignment, vibration, and air conditions matter when one is trying to time a journey that lasts only microseconds across a few kilometers. The success showed that light speed is not only an astronomical curiosity, it is a laboratory property that can be probed with ingenuity and patience. The wheel of teeth became a symbol of how counting unlocks constants. 12. A planet-sized ring can test whether Earth is rotating. If two beams of light travel around a closed loop in opposite directions on a rotating platform, they take slightly different times to complete the circuit. This Sagnac effect is used in ring laser gyroscopes where the interference of the two returning beams reveals the rotation rate with exquisite sensitivity. The idea scales from tabletop devices to paths that encircle parts of the planet using optical fibers. The Earth's spin becomes a measurable difference in light travel time. The phenomenon arises because rotation shifts the effective path length in each direction. Light pays attention to geometry and motion, and the result is a phase difference that appears as a moving interference fringe. Aircraft, ships, and drilling platforms rely on compact versions of this device for navigation, where reliability and independence from external references are crucial. The light inside the ring is a tireless pilot that never blinks. Large-scale versions double as geophysical instruments. Earthquakes, tides, and atmospheric pressure changes can modulate the signal by subtly flexing the loop or by altering the refractive properties of the medium. In that sense, a ring laser is both a gyroscope and a stethoscope for the planet. The unbroken rule throughout is that light locks the timing, and timing turns motion into a trace that engineers can read. 13. Light can seem to move faster than light without breaking physics. In certain optical setups, the peak of a pulse can emerge from a medium earlier than it would if it had travelled at the vacuum speed of light. This happens in regions of anomalous dispersion, where the shape of the pulse is reshaped so that the maximum shifts forward. The group velocity that describes the movement of the pulse envelope can exceed the vacuum speed of light or even become negative. Yet no information outruns the limit, because the front that carries new content does not advance faster than allowed. Experiments demonstrate this with carefully prepared gain media and with clever filtering. The appearance can be dramatic when a detector records a peak that arrives early. The explanation lives in the mathematics of superposed waves. The medium amplifies some parts of the spectrum and attenuates others, which shifts where the maximum appears without helping a true signal get ahead of a light front. The illusion is a lesson in the difference between shapes and messages. The distinction preserves causality. Communication relies on changes that cannot be predicted from previous parts of the signal. Those changes sit on the front and obey the vacuum speed limit. Engineers who design high-bandwidth systems take these nuances into account to prevent misleading interpretations of phase and group measurements. The result is a deeper respect for how light encodes information and how media tamper with that encoding. 14. A laser can be slowed to a walking pace. Under special conditions, such as in ultra-cold atomic gases, the effective speed at which a light pulse moves through the medium can be reduced to meters per second. The technique couples the light to matter waves in a way that stores and retrieves the pulse while preserving its shape and phase. What appears to be slow light is a controlled dance in which the medium holds the information and then hands it back out, all while respecting the vacuum speed limit for true signals. This control opens paths to quantum memories and to devices that synchronize photons for interference-based computation. By pausing and releasing light with high fidelity, researchers can make different photons indistinguishable or can buffer signals for precise timing. The demonstration that light can be shepherded so gently that it nearly stops without losing identity is a landmark in the art of coaxing coherence from complex systems. The phenomenon also clarifies the meaning of speed in dispersive media. The energy and the information can reside partly in the atoms during the slow passage. When the coupling is turned off, the stored excitation can remain in matter and then be read out as a fresh light pulse that carries the original content. The road that looked clogged is in fact a side street where custodians keep the package safe before sending it on. 15. The colour of starlight shifts because time and motion reshape it. When a star moves away, its spectral lines slide toward longer wavelengths, and when it moves toward the observer, the lines shift shorter. This Doppler shift for light does not require a medium. It arises from the structure of space-time and from how intervals of time and space are measured in different frames. The shift turns colour into a speedometer and allows astronomers to weigh planets through the wobbles they induce in their stars. Over cosmological distances, the expansion of space stretches the wavelengths of light from galaxies so that emission born in the ultraviolet arrives as infrared. The redshift is then not only a measurement of motion, but a record of how space itself has grown during the journey. Spectra of distant supernovae and of the cosmic microwave background become maps of the history of expansion written in the language of colour and frequency. Local gravity adds subtle effects. Light that climbs out of a gravitational well loses energy and shifts to longer wavelengths, while light that falls in gains energy and shifts shorter. These gravitational redshifts and blueshifts are small near stars and large near compact objects. Precision spectroscopy detects them and uses them to test theories of gravity and to measure masses. In all cases, the vacuum speed of light mediates how frequency, time and motion are braided together. 16. The fastest signal in nature and the limit of information match one number. The maximum rate at which information can be transmitted through any channel with a given bandwidth and power is bounded by results from information theory. In physical realizations, the constraints reduce to the same constant that limits signal speed. Photons that carry messages cannot be organized to deliver content ahead of a light front, and even clever encodings that pack bits densely into phase and amplitude remain inside the boundary. Quantum protocols do not loosen this leash. Entanglement correlations appear across space without delay, yet they cannot be harnessed to convey messages without a classical channel that moves no faster than the vacuum speed of light. The requirement preserves the agreement among observers and prevents contradictions in which messages appear before they were sent. The fastest messenger and the sternest rule for communication are two faces of the same constant. In practice, engineers design fibre networks and free space links with margins that respect this physics. Relay distances, amplifier placements, and error correction windows are chosen with light time in mind. Financial trading firms that seek the quickest routes between cities lay cables along straight paths and use microwave links across mountains, all to shave milliseconds that are ultimately pinned by light. Even human impatience cannot outrun the limit that makes the world coherent. 17. The night sky is not dark for the reason most people think. If the universe were infinite and static and filled uniformly with stars, the night sky would blaze because every line of sight would end on a stellar surface. The darkness we observe means that at least one assumption fails. The expansion of the universe and the finite age of the stars ensure that much of the light has not had time to arrive, and that what does arrive is stretched and diluted. The vacuum speed of light turns the sky into a record of history rather than a paint bucket of brightness. This resolution of the old paradox interlocks with background radiation that bathes space. The cosmic microwave background is the cooled remnant of an early hot epoch and arrives today as a nearly uniform glow. Its faintness and its spectrum match an origin in a young universe where light scattered repeatedly before decoupling and flying freely. The sky is dark because clocks and expansion collaborate to keep most of the ancient light out of the visible band. The darkness is therefore informative. It is not an absence but a signature that the cosmos has a timeline and that the horizon of the observable region is finite. Every telescope that collects faint photons is gathering clues about how long light has been travelling and how far the front of information has advanced. The vacuum speed of light sets the pace, and the night yields to those who learn to read its silence. 18. Distance across the universe is measured with light echoes. Explosive events such as supernovae and flares illuminate surrounding dust and gas, which then scatter the light toward observers after delays set by geometry. By watching the expanding rings and arcs of these light echoes, astronomers reconstruct distances and three-dimensional structures. Time becomes depth because the vacuum speed of light turns path lengths into clocks. The technique links images to timelines in a way that no static picture can match. Light echoes work on scales from the parsec-sized clouds around stars to the kiloparsec structures in galaxies. They unaffect the intrinsic brightness assumptions that often complicate distance ladders. Instead, the method uses geometry and timing that do not require knowing how bright the original flash was. Each echo is a delayed answer to a question posed by the burst, and the pattern of answers paints a map that only light can render. The method also serves as a cross-check on their own cosmic yardsticks. When multiple techniques converge on the same distance, confidence grows in models of expansion and structure formation. The echoes remind observers that the universe communicates in delays and reflections, and that patience is the first virtue for those who ask large questions. The stopwatch built into light turns the cosmos into a classroom for geometry. 19 Po. A black hole delays light as if space were thicker near it. A signal that passes near a massive body arrives later than it would have if space were flat. This gravitational time delay, often called Shapiro delay, is not due to a longer path through matter, but to the way mass curves space-time and stretches the time component along the route. When signals from spacecraft or pulsars skim the sun or a planet, careful timing reveals the extra delay that matches predictions from the geometry of gravity. The effect becomes significant near compact objects. Pulsar timing arrays that monitor the rhythmic beacons of neutron stars see how intervening masses change the tempo briefly when the line of sight passes close to them. These delays are sensitive tools for mapping gravitating structures that are otherwise hard to detect. The light is not slowed by friction. It is crossing a region where the clock that measures its travel ticks differently. Close to a black hole, the accumulated delay contributes to the visual ring that telescopes resolve. Photons that take looping paths linger near the hole and emerge as images that are both delayed and demagnified. The glow encodes time as well as brightness. Every pixel in such an image has a history that includes a negotiation with gravity over how quickly time should pass along the way. 20, the shortest time that makes physical sense, is set by light. The Planck time is a combination of constants that includes the vacuum speed of light, the gravitational constant, and the quantum of action. It marks a scale at which the known theories cease to provide a clear picture of events. Shorter than this interval, the very idea of time as a smooth parameter may fail. The presence of the vacuum speed of light in the recipe shows that the ultimate granularity of time, if it exists, is tied to the same constant that limits signals. This does not assert that time is made of ticks of that size. It says that attempts to describe nature at finer scales using current frameworks run into contradictions or infinities. The combination of constants is a lighthouse that warns ships away from shoals where new physics is required. Researchers aim to approach this shore through clever measurements that look for signatures in high-energy cosmic events or in precise laboratory systems. If a deeper layer exists where space-time is emergent, it will likely still include a limiting speed woven into its structure. The constant has proved robust across enormous ranges of energy and scale. It appears in every theory that respects relativity and in every device that measures reality with light. Whether time is smooth or grainy, the maximum speed stands as the rule that prevents the story of the universe from tangling itself. 21. A single photon interferes with itself and draws a map of possibilities. In carefully arranged experiments, a single quantum of light travels along paths that are kept indistinguishable and paints an interference pattern over time. Each detection event is a solitary dot, yet after many repetitions, a fringe pattern emerges that matches the wave description. The result shows that nature does not force a photon to choose one classical route when alternatives cannot be told apart. Probability amplitudes add and subtract, and the screen becomes a record of how possibilities were allowed to combine. Changing which path information leaks into the environment erases or restores the fringes. If a traceable mark tags the route, the interference fades because the alternatives are no longer indistinguishable. Remove the tag and the pattern returns even though the energy arrives one quantum at a time. The apparatus is not persuading the photon to dither. It is shaping the conditions under which the laws of addition for amplitudes apply. The map is not only pretty, it calibrates metrology and sensing. Interference from single photons underpins measurements of tiny phase shifts that reveal distances, refractive changes, and forces. The faintest possible light becomes a surveyor's tool that works because the quantum rules care about what could have happened as much as does about what did happen. The vacuum speed of light remains the messenger, while the superposition principle writes the signature. 22. Space itself has a refractive index in strong fields. In regions where electromagnetic fields approach extreme strengths, quantum fluctuations of charged particles modify the propagation of light. The vacuum behaves like a medium whose response depends on polarization and field direction. The effect is tiny under ordinary conditions, yet becomes significant near neutron stars and magnetars, where magnetic fields reach values that bend the rules of intuition. Light can split into modes that march at slightly different speeds and rotate polarization as they travel. Observations of polarized signals from compact objects test these predictions. When a beam crosses a magnetized vacuum, the plane of polarization can twist in a way that cannot be explained by gas alone. Laboratory searchers strive to detect the same behavior with high-finesse cavities and intense fields, teasing out minute phase shifts with patience and careful isolation from noise. The challenge is steep, and the prize is a direct glimpse of the quantum texture of emptiness. The lesson is that empty is a convenience term. On the deepest scales, space seethes with virtual excitations that briefly borrow energy and return it as allowed by quantum accounting. Strong fields nudge these excitations into patterns that a passing photon can feel as an altered index. The change remains consistent with the limiting role of the vacuum speed of light for information fronts, while hinting at layers of structure beneath everyday emptiness. 23. Light travels slower in glass because atoms pause the wave again and again. Inside a transparent solid, the electromagnetic field drives electrons in the material to oscillate. These driven motions radiate in step with the original field, but with slight delays that depend on frequency. The superposition of the original wave and the re-radiated fields forms a combined wave that crawls through the medium at a reduced speed. No single photon is trapped in a literal queue at each atom. The whole process is a collective delay emerging from coherent response. Dispersion appears because the electrons respond differently to different colors. Near atomic resonances, the delay grows, and the refractive index climbs. Far from those resonances, the electrons lag less, and the index falls. This frequency dependence spreads short pulses and splits white light into colors in prisms and rainbows. The path through a material is therefore both a corridor and a filter that encodes the material's spectrum into the light that emerges. Losses and scattering add texture to the story. Perfectly transparent media are ideals that real glasses and crystals approach but never fully reach. Tiny impurities and structural irregularities steal energy and blur phases. Engineers tame these imperfections through purification and careful growth so that fiber optics can guide light for hundreds of kilometers with small attenuation. Even then, the message moves slower than in vacuum because the dance with matter takes time. 24. The meter definition made precise length possible anywhere on Earth. Replacing a metal bar with a definition based on the vacuum speed of light and the duration of a second transformed metrology, laboratories no longer chase the temperature and strain of a physical artifact. They compare stable laser frequencies to atomic transitions and count time to mark distances. The same procedure works in mountain labs, sea-level workshops, and spacecraft assembly rooms because the constant that anchors it is universal. This shift enabled leaps in technology. Lithography for microchips relies on rules measured in nanometers and demands that those rules match from factory to factory. Geodesy maps the planet with satellite ranging and needs distances that do not drift with the seasons. Scientific instruments that compare wavelengths across continents can trust that length standards remain synchronized because they are born from light and time rather than from alloy and storage. Uncertainty budgets shrank and collaboration grew. When an interferometer in one country reports a path difference and another team reproduces the setup elsewhere, they are speaking the same language. The meter became democratic because any group that masters clocks and optics can build it. The choice also acknowledges a philosophical point. The most reliable rulers are those that rely on properties of nature that appear constant across both place and era. 25. Why nothing with mass can reach the speed of light. As an object with mass accelerates, each increment of speed demands more energy than the previous one. The equations that connect energy, momentum, and velocity show that the required energy rises without bound as the speed approaches the vacuum speed of light. The kinetic energy does not merely increase, it diverges, turning the last stretch into an impossible climb for finite engines. The boundary is not a hurdle to be cleared with better fuel, it is a wall built into space-time. Mass brings inertial resistance that grows with motion in a way that cannot be tamed by clever design. Even particles smashed in giant accelerators that span kilometers remain shy of the limit despite energy inputs that stagger imagination. Their lifetimes stretch through time dilation, their paths curve under magnetic steering, and their signals whisper the same verdict. The limit is both a guardian of causality and a mechanic that keeps the mathematics consistent. Thinking in geometric terms clarifies the ban. World lines for massive objects tilt within the light. A cone, and can never become light-like. To change the category would require rewriting the light cone itself or allowing proper time to vanish for a massive traveller. Neither move is allowed by the rules that keep cause and effect orderly. The limit is therefore not an engineering failure. It is the signature of the structure that makes motion meaningful. 26. The faster a spacecraft moves, the more kinetic energy becomes mass-like. Energy and mass are two measures of the same physical content under different circumstances. When a vehicle gains kinetic energy at high speed, the total energy that curves space-time and resists acceleration increases. In that sense, the kinetic portion contributes as mass-like content, even though the rest mass remains constant. The craft does not fill with new material. It carries more energy that gravity and inertia treat with similar seriousness. This shows up in how momentum scales. At low speeds, momentum adds linearly with mass and velocity. Near the vacuum speed of light, the relation includes the growing total energy, and therefore does not climb in a simple proportional way. Engines that attempt to push harder find that less of their effort translates into additional speed and more into this mass-like store. The climb becomes steep and the horizon of light speed recedes like a mirage. The insight threads through astrophysics as well. Hot gases in clusters, beams in jets, and radiation trapped in cavities all weigh more than their cold or dark counterparts because of the energy they hold. When light bounces inside a mirrored box, the box becomes heavier by the amount of energy trapped within. The same unification that tells the spacecraft to respect the limit also tells gravity to count stored energy as part of what it must curve. 27. The colour of a sunset is a history of photon scatterings. As the sun nears the horizon, its light crosses a longer path through the atmosphere, meeting molecules and tiny particles that scatter shorter wavelengths more efficiently. Blue and violet are diverted from the direct line to the eye, leaving the direct beam enriched in red and orange. Larger particles from dust or aerosols add their own broader scattering that mutes or deepens colours depending on size and abundance. Each hue is a ledger of encounters between photons and air. The same physics explains why the sky overhead looks blue at midday. Short wavelengths scatter in all directions and fill the dome with a soft glow even when the sun itself is white. At twilight, the path lengths and particle distributions produce gradients that shift minute by minute, revealing layers in the atmosphere as if they were bands in a mineral. The spectacle is not a paint applied by the sun, it is a negotiation written during travel. Volcanic eruptions and fires can seed the air with particles that change sunsets for months. Observers at different latitudes read different chapters of the same story because the angle and thickness of the air vary with location and season. The vacuum speed of light does not slow during this passage, yet the repeated scatterings carve a long path that selects colours. The horizon becomes a textbook that speaks in scarlet and gold. 28. A lighthouse beam can sweep across the moon faster than light. When a distant surface is scanned by a rotating spotlight, the bright spot can move across that surface at an apparent speed that exceeds the vacuum speed of light. No rule is broken because the illuminated points are not in physical contact with one another. Each point lights up when its own photons arrive, and no single object or message moves along the path of the sweeping spot. Apparent motion does not carry information between neighbouring points. Astronomers use similar geometry when mapping with rapidly steered beams. A radio dish that slews across a planet can create a track of illumination that would correspond to a superluminal spot if translated into a ground speed. Yet every part of the target receives a signal only from the transmitter and only when aimed directly. There is no sideways handoff that would be required for a true faster-than-light messenger. This distinction is crucial in interpreting high-speed phenomena. Pattern speeds, interference fringes and shadow edges can all move in ways that outpace the vacuum speed of light. The front that introduces new information, the first arrival at a point not previously illuminated, always honours the limit. Understanding this boundary keeps intuition aligned with the rules, and prevents illusions from turning into incorrect claims about broken physics. 29. The delay when a spacecraft talks to Earth is light time and nothing else. Signals between Earth and a distant probe take a time determined almost entirely by the distance divided by the vacuum speed of light. Electronics inside the spacecraft add microseconds and ground systems add small processing lags, but those are tiny compared with the minutes or hours that space introduces. Mission controllers plan maneuvers and command sequences, with this one fact always in front. Every conversation is a message sent into the past of the other party. Navigation exploits the delay. By timing two-way exchanges and by using the frequency shift of the return signal, teams deduce velocity and range with exquisite precision. The probe and the planet become endpoints of a long optical or radio ruler. Gravity fields reveal themselves as tiny changes in the delay pattern as the spacecraft flies by or orbits. The mathematics is clean because the dominant term is the immutable speed of the messenger. This discipline changes the art of piloting. There is no real time joystick for a craft near another world when light time is long. Autonomy on board handles fast contingencies while Earth plans and reviews with deliberate care. The limit simplifies and complicates at once. It removes the illusion of instant control and replaces it with a cadence that missions learn to respect. The vacuum speed of light becomes both partner and referee. 30. The most precise rulers are made of oscillating light. Optical clocks and frequency combs turn the rapid oscillations of laser light into ticks that can be counted and compared. By stabilizing a laser to a narrow atomic transition, and by linking optical frequencies to radio frequencies through a comb of evenly spaced lines, metrologists build timekeepers that drift less than a second over the age of the universe when extrapolated. Distance measurements then ride on time by multiplying by the vacuum speed of light. Interferometers that compare path lengths at the level of fractions of a wavelength sent. Motions smaller than the size of an atom. Gravitational wave observatories, displacement sensors for inertial navigation, and dimensional metrology and manufacturing all use this power. The ruler is not a rod. It is a phase difference measured at detectors that translate light's rhythm into numbers. The environment must be calmed because thermal and seismic jitters try to add their own music. Frequency tools knit laboratories across continents. A stabilized fiber link can deliver a reference tone from one institute to another, letting teams compare clocks separated by oceans. Satellite links extend the reach further. The language they share is the periodicity of light, steady and universal. When the count is trustworthy, length follows as time multiplied by a constant. The most perfect ruler is therefore a song that never wavers. 31. Light reveals planets by timing the star they eclipse. When a planet crosses in front of its star, the brightness dips in a pattern that repeats with the orbital period. The start and end of the dip are marked by the light clock of the star system, with a precision that grows as more transits are gathered. Small differences in timing hint at other worlds tugging on the transiting planet, and the exact shape of the dip tells the ratio of sizes between planet and star. The path of light through the planetary atmosphere also leaves a fingerprint because some colours are absorbed more than others during the crossing. Beyond the first planet, timing variations map gravitational interactions that would otherwise be invisible. If two planets are near a resonance, their mutual pulls speed up and slow down the transit schedule by amounts that can be measured with patient watching. The entire architecture of a distant system emerges from a chronicle written only in light that dims and recovers according to a celestial dance. The method stretches across the galaxy because it needs no resolution of disks or surfaces. It asks only for a steady star, a good clock, and the immutable speed that carries the signal. Combined with radial velocity measurements from spectral shifts, the timing pins down densities and allows comparisons between rocky bodies and gaseous giants. Worlds once imagined only in stories are now catalogued by reading the calendar they inscribe on their parent light. 32. The cosmic speed limit locks in the order of events. When two happenings are separated by distances that require light time to connect, their order can shift for observers in different states of motion. Yet if one event can cause the other through a signal, every observer agrees on that order. The vacuum speed of light defines the cones within which cause can reach effect and outside which no message can pass. This geometry prevents contradictions that would arise if an effect could slip ahead of its cause for someone moving differently. Practical systems rely on this discipline. Distributed computers, satellite networks, and financial exchanges must sequence operations in a world where signals are not instantaneous. Protocols set tolerances based on light time to ensure that acknowledgements and remits occur in windows that cannot be spoofed by long routes or delayed reflections. The physics behind relativity becomes a design guide for consistency. In astronomy, the same logic helps untangle complex transients. When a neutron-star merger produces both light and gravitational waves, the arrival difference is interpreted through propagation across cosmic distances at nearly the same speed. The concordance reinforces the rule that makes a shared timeline meaningful. The constant preserves a fabric where stories can be told without knots that break understanding. 33. Quantum entanglement does not send messages faster than light. Pairs of photons can be created in states where their properties are correlated in ways that defy classical explanation. Measuring one photon immediately constrains what can be said about the other, even when they are far apart. The temptation is to imagine a secret signal racing between them faster than light. Detailed analysis and experiments show that no usable information is conveyed by the correlations alone. To compare results and extract a pattern, a conventional message limited by light is still required. Bell tests with fast and random measurement choices close loopholes that once allowed alternative explanations. Detectors placed far enough apart ensure that one device cannot influence the other by any signal that respects the speed limit during the measurement window. The observed correlations remain, yet attempts to encode a bit by choosing a measurement on one side fail when only the partner's local outcomes are viewed. The result respects both quantum strangeness and relativistic order. Entanglement links possibilities in a way that challenges intuition, while the impossibility of faster-than-light messaging protects causality from paradox. Quantum networks that will one day share keys in distributed states will still schedule their classical coordination channels according to light time. The weirdness becomes a resource without becoming a loophole in the rulebook. 34. The universe expands in a way that can separate galaxies faster than light. Distant galaxies can recede from each other at apparent speeds greater than the vacuum speed of light because the fabric of space between them is stretching. No object is moving through space at a forbidden speed. The distance grows because the scale of the map itself grows. Light emitted by a far galaxy must cross an ever-lengthening path and arrive stretched into longer wavelengths that encode the history of that expansion. This distinction matters for horizons. Regions beyond a certain distance cannot exchange signals now because the expansion rate makes the gap widen faster than light can bridge it. The observable universe is therefore bounded not by walls but by a limit set by time and growth. What lies beyond remains causally disconnected, not because of a barrier but because messages cannot catch up in an ever-enlarging arena. Measurements of supernovae, background radiation, and galaxy clustering have traced how the rate of expansion has changed. The discovery that the expansion is accelerating implies a component of the cosmos that exerts pressure with unusual properties. Even in that scenario, the rule for local signals remains the same. Light still governs communication within each neighborhood, while the stage on which the play unfolds slowly resizes itself. 35. There is no global now when light is the referee of time. Simultaneity depends on motion. Two observers in relative motion who synchronize clocks with light pulses will not agree on which distant events are happening at the same time. Each observer builds a grid of space and time using the same procedure, yet the slices of constant time tilt relative to each other. The vacuum speed of light as a constant enforces this tilt and makes a single universal present impossible across vast regions. The absence of a global now is not a defect. It is the price of keeping the laws of physics identical in all inertial frames. Local experiences remain orderly and consistent because all observers agree about events that can influence or be influenced by one another. The disagreement appears only when comparing separate places without direct causal ties. The structure permits different valid descriptions rather than chaos. Technology navigates this landscape by choosing conventions. Global positioning systems adopt specific definitions of coordinate time and correct for motion and gravity so that receivers interpret signals in a common frame. Engineers respect that their chosen now is a useful tool rather than a fact of nature. The universe offers only local nows stitched by light into a coherent but frame-dependent fabric. 36. How the aberration of starlight proved Earth is moving. In the 18th century, astronomers noticed that the apparent position of a star traces a tiny ellipse over a year. not because the star wanders, but because light arrives at a finite speed while Earth moves in its orbit. The telescope must be tilted slightly into the direction of motion to catch the rain of starlight, an effect called aberration. The size of the ellipse depends on the ratio of Earth's orbital speed to the vacuum speed of light. This phenomenon provided an early and elegant proof that Earth is not stationary. It linked celestial observation to terrestrial motion without requiring parallax, which was too small to measure with his instruments of the time for most stars. The aberration angle became a ruler for velocity, allowing a measurement of the ratio that pointed towards the true scale of light speed when combined with known orbital speeds. Modern instruments still account for aberration when building precise catalogues. Space telescopes and radio arrays correct positions according to the motion of Earth and of the observatory itself. A simple geometric idea discovered with early telescopes remains a daily tool at the frontiers of precision astronomy. The sky appears stable, yet the reception of its light is a negotiation with motion that never rests. 37, starlight that skims the sun, arrives late by a measurable pinch. Signals that pass near the sun take slightly longer to reach Earth than they would if they travelled through flat space-time. The delay comes from the curvature created by the sun's mass, which stretches the time component along the path. Early tests used radar echoes from planets during superior conjunctions, while modern observations use spacecraft tracking and pulsar timing to resolve the tiny extra time. The effect is consistent with the predictions of curved geometry. This delay is more than a curiosity. It constrains parameters of gravitational theories and helps calibrate models of the solar corona that also affect radio propagation. By separating the gravitational contribution from plasma effects, scientists refine both the map of spacetime near the Sun and the understanding of the hot gas that the Sun ejects. Each careful campaign turns a path of light into a probe for both gravity and astrophysical weather. Near compact objects, the same principle magnifies. A pulsar orbiting a heavy companion shows timing residuals that contain both gravitational redshift and propagation delay. The combined pattern tests the structure of the theory under conditions far stronger than any lab can produce. In every case, the message arrives when spacetime permits and the stopwatch records how geometry modulates the journey. 38. How a spinning platform scrambles light travel times. On a rotating disk, two light beams sent in opposite directions around a loop return at different times. The difference creates a phase shift that appears as moving interference fringes when the beams are recombined. This Sagnac effect anchors ring laser gyroscopes and fiber optic gyros that report rotation rates with remarkable stability. The device does not rely on external references and therefore remains useful in environments where magnetic or satellite cues are unreliable. The underlying reason is kinematic rather than gravitational. Rotation changes the effective path length because the apparatus turns while the beams travel. Even if the index of refraction inside the loop is uniform, the geometry of motion creates a built-in asymmetry between the two directions. The result scales with the enclosed area and the rotation rate, which is why larger loops are more sensitive and why compact devices use long-coiled fibers to simulate large areas. Applications range from aircraft inertial navigation to monitoring tectonic motions. Arrays of large ring lasers have recorded signals from earthquakes and have helped model the coupling between atmosphere and solid Earth. The same physics that controls a tabletop instrument also reads the planet's murmurs. Light is the courier, the loop is the arena, and rotation writes its signature in timing differences that never tire. 39. The color of cosmic microwave light proves space once was fire. Every direction on the sky glows with a faint microwave signal that follows an almost perfect thermal spectrum. The temperature of this glow is a few degrees above absolute zero, yet its shape tells of an origin in a much hotter and denser epoch, when light and matter were tightly coupled. As the universe expanded, wavelengths stretched and the once brilliant light cooled into microwaves while preserving the smooth curve that only a thermal process can create. Small variations in the glow carry deep information. Tiny ripples in brightness and polarization trace sound waves that rang through the early plasma. From their pattern, scientists infer the composition of the cosmos, the curvature of space, and the timeline of expansion. The signal is not a local fog. It is a page from a universal diary that survived intact because nothing can erase the imprint written into the fabric of space by ancient light. The constancy of the speed at which this light propagates underlies the interpretation of its map. Distances on that map are angles on the sky today, and the conversion between early physical scales and current angular scales uses the known propagation of light through an expanding medium. The microwave background stands as a fossil that links the smallest ripples to the grandest structures we see now. 40. Why a mirror reversal is not what most minds imagine. A flat mirror does not swap left and right in the way casual intuition claims. It reverses front and back along the axis perpendicular to the surface. The confusion arises because people often imagine themselves turning to face the mirror and then compare the turned body to the reflection. The turn introduces a left-right exchange that the mirror itself did not perform. The mirror simply flips the direction along the line of sight while leaving up, down and left-right intact. Light rays obey the rule that the angle of incidence equals the angle of reflection. A point on a face and its mirror counterpart sit at equal distances on opposite sides of the surface plane. When a person raises the right hand, the reflection appears to raise the left only because the observer imagines standing in the place of the reflected person after a turn. Without that mental rotation, the pattern is a simple front-back reversal. Understanding the geometry clears up many puzzles about mirror writing and optical systems. Periscopes, kaleidoscopes, and corner cube reflectors exploit predictable reversals to send light back along chosen routes. The mirror is a precise tool that obeys a single elegant rule. Minds project extra steps into the scene and then blame the surface for tricks it never played. 41. The edges of a fast-moving object appear rotated, not squashed. At relativistic speeds, the image of an object is not a simple contraction, but a distortion caused by light travel time. Light from the near side reaches the observer sooner than light from the far side, so the image accumulates signals emitted at different times. The combination makes the object appear rotated, an effect known as Terrell rotation. A sphere racing past would look almost normal in shape, but with its far side unexpectedly visible. This visual rotation does not contradict Lorentz contraction, measured in the object's own frame. It is a difference between geometry and perception. Photons carry a record of emission time as well as direction, and when those emissions are reassembled in an observer's camera, the patchwork of delayed arrivals paints a twisted but consistent picture. The effect has practical implications in visualization and astrophysics. Artists who render near light-speed travel must compute these delays to avoid misleading flat distortions, and simulations of jets or accretion disks use the same math to predict what telescopes might actually see. The universe hides its rules in appearances that reward patience and careful reconstruction. 42. A moving clock and a stationary clock disagree and both are correct. Two identical atomic clocks will accumulate different amounts of time if one travels at high speed and returns to meet the other. The traveller's path through spacetime has less proper time between departure and reunion. Each clock, however, measures its own ticks locally and finds nothing unusual. The disagreement arises not from malfunction but from geometry. Spacetime allows multiple paths between events with different lengths in time, just as a landscape allows roads of different distances between towns. The twin experiment dramatizes this reality. A person who journeys at a substantial fraction of light speed will age less than a sibling who stayed home. The asymmetry enters when the traveller turns around. Acceleration changes reference frames and breaks the symmetry that pure relative motion would preserve. The result is measured today with push-test clocks flown on aircraft or satellites that record the small differences predicted a century ago. This phenomenon is not a theoretical curiosity. Navigation systems must compensate for time dilation from both motion and gravity, and particle lifetimes in accelerators reveal the same arithmetic. Each clock ticks honestly within its own world line, and the mismatch after reunion is nature's reminder that time is not universal but personal to motion and gravity. 43. Neutrinos almost match light speed, yet never quite reach it. Neutrinos, the elusive particles born in nuclear reactions and stellar explosions, travel incredibly close to the vacuum speed of light because their masses are tiny but not zero. Early hints once suggested superluminal motion, but refined experiments using synchronized clocks and long baselines proved otherwise. The particles arrive fractions of a microsecond later than a photon would over the same distance, a delay consistent with their minuscule mass. This near-light behavior allows them to escape dense environments where photons would be trapped. Supernovae broadcast neutrinos that reach detectors before the optical flash because they pass through the outer layers unhindered. Their timing still obeys the cosmic limit, and measuring that timing helps estimate the neutrino mass more precisely. These findings underline that nature grants different messengers Slightly different privileges, but upholds the ultimate ceiling for all. The vacuum speed of light remains undefeated, and the neutrino's tiny lag is a signature of matter's stubborn weight. Across cosmic distances, that sliver of delay encodes both the identity of the particle and the reliability of the universal limit. 44. The radius of the observable universe is measured in light years of time. Because information cannot reach us faster than the vacuum speed of light, the observable cosmos is bounded by how long light has had to travel since the Big Bang. Each direction stretches roughly 46 billion light years, even though the universe is only about 14 billion years old. Expansion of space makes the current distance larger than the simple product of speed and age. The boundary is not a wall but the edge of visibility, beyond which signals have not yet arrived. This horizon defines what we can study. Every telescope, no matter how powerful, looks back along a cone of light that starts at the observer and widens into the past. Galaxies nearer the limit appear younger because their light left when the universe itself was young. What lies beyond may exist but remains causally separate for now, waiting for time to make contact. Cosmological models use this horizon to normalize densities and to estimate total energy content. When we say the universe is flat or curved, we mean within this observable bubble measured by light's reach. The horizon grows slowly as cosmic time passes, but the principle stays fixed. Light sets the frontier of knowable reality. 45. A laser can sculpt matter with momentum carried by light. Each photon bears momentum equal to its energy divided by the vacuum speed of light. When countless photons strike a surface, the combined push, though small, exerts measurable pressure. Focused lasers exploit this to trap, move, or ablate material with exquisite control. The momentum transfer can levitate microscopic spheres or carve patterns in metal without physical contact. Radiation pressure bridges optics and mechanics. In space, it nudges comet tails away from the sun and propels solar sails that use sunlight as propellant. In laboratories, optical tweezers harness gradient forces from focused beams to hold bacteria or manipulate DNA molecules, translating the abstract constant of light speed into a tangible touch. Even at industrial scales, the principle holds. Laser machining relies on the balance between energy deposition and recoil from vaporized material. The boundary between illumination and force disappears, revealing light as both messenger and sculptor. Momentum and speed intertwine so closely that a beam becomes an invisible stream of hands shaping matter. 46. Light carries pressure that pushes on comet tails. Sunlight streaming through the solar system transfers momentum to dust grains and comet comas. The smaller and lighter the particles, the more the push competes with gravity, driving tails that point away from the sun regardless of the comet's path. Gas tails trace charged interactions with the solar wind, while dust tails follow the steady radiation pressure from photons travelling at the light speed. This pressure is minute compared with gravity, yet persistent over time. It sorts dust by size and sculpts delicate structures observed by telescopes as comets approach the sun. The same mechanism cleans into planetary space by sweeping fine debris outward. In the long view, light becomes a gardener that prunes and shapes the solar system. Designers of future spacecraft adapt this force intentionally. Thin reflective sails can harvest radiation pressure for propulsion, trading thrust for infinite fuel economy. The concept transforms sunlight into a constant engine powered by the immutable flow of photons, a slow but eternal wind born from the speed of light itself. 47. A photon has no rest mass within experimental limits. All measurements so far find that the photon's rest mass, if any, is below detectable thresholds, smaller than 1 part in billions of an electron's mass. This near-zero property ensures that the electromagnetic waves propagate exactly at the vacuum speed of light, and that the range of the force is infinite. A finite mass would make the force fade over distance and alter the behavior of magnetic fields across galaxies. Sensitive experiments test for such deviations. They watch planetary magnetic fields, examine radio waves from distant pulsars, and measure how Coulomb's law holds in the laboratory. The absence of anomalies constrains the photon mass ever more tightly. Each null result reinforces the symmetry principles embedded in the equations of electromagnetism. If a tiny mass were someday detected, it would revolutionize theory, introducing a cutoff in field behavior and possibly linking light to deeper structures. For now, the photon remains the quintessential massless messenger, the one entity that always moves at the same ultimate speed regardless of who measures it. By the way, if you like and subscribe to my video, this is the most effective way to support me. 48. Vacuum polarization can tweak how light moves near extreme fields. Quantum electrodynamics predicts that empty space teems with virtual particle pairs that flicker into and out of existence. Near colossal electric or magnetic fields, these pairs polarize the vacuum, slightly altering how real photons propagate. Light may bend or change polarization even without matter present. The effect is subtle, orders of magnitude beyond ordinary laboratory reach, but astrophysical giants like magnetars provide natural testbeds. When photons traverse such regions, the polarization rotation they experience carries information about the unseen fields. Observations of X-ray and gamma-ray polarization offer the first hints that this quantum vacuum birefringence exists. Laboratory versions using ultra-intense lasers are being prepared to reproduce the effect on Earth, where detectors must sift faint phase changes from the overwhelming noise. This phenomenon connects quantum fluctuations to cosmic structure. It shows that even the vacuum's transparency is conditional, shaped by energy density, yet the fundamental speed limit survives untouched. The modification affects phase and group velocities, but not the front speed that governs causality. Space, it seems, whispers when stressed but never screams. 49. The Scharnhorst proposal hints at an almost impossible speed-up. Theorists once examined light travelling between two closely spaced conducting plates, the same geometry that produces the Casimir effect, and found that the altered vacuum modes might let signals move infinitesimally faster than in unrestricted space. The predicted excess is unimaginably small, far beyond experimental reach, and entwined with assumptions that prevent any real violation of causality. In this scenario, fewer virtual pairs exist between the plates, slightly reducing the vacuum's optical density. Calculations yield an advance so minute that even if realized, it would not allow information to outrun a light front. The structure of relativity remains intact because the adjustment concerns the phase of waves, not the timing of messages. The idea persists as a theoretical curiosity, reminding physicists how subtle boundary conditions can alter quantum fields. It does not open a highway for superluminal travel. Instead, it demonstrates the robustness of the cosmic speed limit under the imaginative assaults. Light may twitch under confinement, but logic keeps its crown. 50. The slowest light pulses reveal the dance between matter and field. In ultra-cold atomic gases, researchers have slowed light to walking pace, or even brought it to a halt by coupling it to collective excitations of atoms. The technique, known as electromagnetically induced transparency, turns a normally opaque medium into one that stores the electromagnetic information as a pattern of atomic coherence. When the control field is restored, the stored state releases the photon pulse, preserving its shape and phase. This choreography does not contradict relativity, because the true information front still moves at the vacuum speed of light. What changes is the group velocity, the rate at which the envelope of energy and phase moves through the medium. The delay arises from the interaction between photons and the induced dipoles in the gas, a temporary handoff that behaves like a pause button for light. Applications reach from quantum communication to precision timing. Slow light devices act as buffers, synchronizing signals in optical circuits and enabling experiments on fundamental coherence. The spectacle of light nearly stopping in its tracks serves as a reminder that velocity in matter is a property of interaction, while the ultimate cosmic limit remains untouched. 51. Interplanetary navigation is geometry written in light travel time. Every spacecraft in the solar system finds its position not by sight, but by the ticking of radio waves that move at the vacuum speed of light. Ground antennas send coded signals, and when the spacecraft responds, the round-trip delay reveals distance to within meters even across hundreds of millions of kilometers. The system works because the signal's speed is fixed and known, turning time into distance with perfect simplicity. This method lets flight controllers draw invisible triangles between Earth and probes, determining not only how far away they are, but also how fast they're moving. The Doppler shift of the returning tone provides velocity, while the delay provides range. When combined across multiple antennas, these measurements yield a three-dimensional fix more reliable than any visual map. The technique does more than navigate. It uncovers gravitational influences of planets, measures masses of asteroids, and tests general relativity through the way signals bend near the Sun. Each mission adds another confirmation that light speed is the ruler of motion. In deep space, geometry is not built of metal rods but of timed echoes, an architecture of patience where every kilometre is counted by photons. 52. Atomic time and light speed make global positioning possible. The global positioning system and its international siblings depend on atomic clocks whose ticks are synchronized to nanoseconds. Each satellite broadcasts its time, and receivers on Earth compute their location by comparing how long the signals took to arrive. Because those signals travel at the vacuum speed of light, every nanosecond of difference equals about 30 centimeters of distance. Accuracy therefore hinges on knowing both time and the constant speed precisely. Relativity correction is built in. The orbiting clocks tick slightly faster due to weaker gravity, and slightly slower due to orbital motion. Engineers tune each clock on the ground so that when in orbit it keeps pace with Earthbound time. Without those adjustments, navigation errors would grow to kilometers within hours. The entire infrastructure works only because physics is predictable down to picoseconds. Each phone and aircraft receiver silently trusts Einstein and the constancy of c with every position fix. The map that guides travellers is a living demonstration that the speed of light is not abstract, it is the metronome of civilization. The skies above beam an orchestra of photons, and every coordinate on Earth is found by listening to their perfect rhythm. 53. A black hole mirror would never send a reflection back. A black hole's gravity bends space-time so severely that within its event horizon all paths point inward. Any light that crosses that boundary can never return to the outside universe. A mirror lowered even slightly past the horizon would reflect only inward, trapping its own reflection forever. For distant observers, the signal would fade and redshift until it froze at the edge, an illusion of eternal hesitation. The impossibility of reflection makes black holes appear truly black, not because they absorb light like soot, but because geometry prevents escape. Even the photon sphere just outside the horizon, where light can orbit in unstable circles, cannot maintain a sustained reflection. Small disturbances send photons either outward to freedom or inward to oblivion. This absolute one-way surface gives black holes their mystery and power. They are boundaries in space-time itself, not in material form. The idea that light, the swiftest traveller, cannot outrun curvature marks the end of simple visualization. The mirror thought experiment captures the essence of the horizon, a place where time and space trade roles and the universe enforces silence. 54. The ring around a black hole is a maze of bent light. Images captured by the Event Horizon Telescope show a bright ring encircling a dark core. The ring is not a solid object, but the projection of countless light paths curved by the black hole's gravity. Photons emitted by hot gas swirl around the hole, some looping once, others multiple times before escaping toward a distant eyes. Each orbit adds delay and magnification, concentrating brightness into a thin, luminous edge. The light that forms this ring carries the history of chaotic motion and extreme energy. Its polarization patterns reveal magnetic fields, while its thickness encodes how the black hole spins. The darkness inside marks the region from which no light can escape, the shadow that geometry itself casts. This spectacle is a triumph of relativity and observation. By reconstructing the timing of radio waves collected from telescopes around Earth, scientists transformed light travel time into a portrait of curved space. The ring is therefore not only a picture of a hole, but also a map drawn by photons obeying the universal limit. What we see is light performing its last possible dance before disappearance. 55. A gravitational wave moves at light speed and proved it across galaxies. When two neutron stars collided in a distant galaxy, detectors on Earth caught both the rippling of space-time and a flash of gamma rays separated by only seconds after travelling over 100 million years. The near simultaneity confirmed that gravitational waves move at the same speed as light within a margin of 1 part in 10 quadrillion. The event united two messengers of the cosmos in a single clock beat. The equivalence vindicated general relativity and ruled out entire families of speculative theories that predicted slower or faster gravity. It also demonstrated that signals born in cataclysmic events remain synchronized over cosmic time, reinforcing the idea that the universe enforces one shared velocity for information. Now, gravitational wave astronomy uses this constant to locate sources and test cosmic expansion. The detectors act as enormous interferometers measuring differences smaller than a proton's width, translating spacetime's tremors into music. Each detection, moving at light speed, confirms that even the waves of gravity march to the same tempo as photons. 56. Gamma-ray bursts test whether light of different colors keeps pace. Cosmic explosions release photons spanning energies from radio to gamma rays. If light of different frequencies traveled at slightly different speeds in vacuum, the arrival times of these photons over billions of years would smear out the burst. Observations show that high and low energy photons arrive almost simultaneously, implying that the vacuum does not disperse light regardless of color to extraordinary precision. This consistency probes possible quantum gravity effects that might alter the structure of spacetime at minute scales. By finding no energy-dependent lag, astrophysicists constrain such theories and reaffirm that C is truly universal across energies. The cosmic laboratory dwarfs anything achievable on Earth, with distances providing an enormous baseline for comparison. Each burst becomes a stopwatch written in gamma rays. By analysing its front edge and tail, scientists look for differences smaller than milliseconds over the cosmic time. Every absence of delay strengthens the belief that the universe's speed limit is not a local rule, but a principle that governs all wavelengths equally. 57. Why a laser pointer on a distant wall can outrun light only in appearance. When you sweep a laser across a faraway surface, the illuminated dot can seem to race faster than the vacuum speed of light. Yet no single photon travels sideways along the wall. Each one leaves the laser at a distinct angle and strikes a new point independently. The moving spot is a sequence of independent arrivals, not a physical object sliding across the surface. The same reasoning applies to searchlights and celestial shadows that appear to streak across clouds or moons faster than any spaceship. Because no information passes from one illuminated point to the next, causality remains safe. The apparent motion is a geometric projection rather than a signal. Understanding this illusion clarifies many viral misunderstandings of physics. Pattern speeds, beam intersections, and points of constructive interference can all exceed light speed without transmitting energy or data. The limit applies to entities that carry influence, not to mathematical abstractions. The laser's wandering dot remains a demonstration of geometry's mischief, not of broken laws. 58. Group velocity can exceed light speed without moving information. In dispersive materials, the different frequency components of a pulse travel at slightly different speeds. When they interfere, the envelope of the pulse, the group, can appear to move faster than the vacuum speed of light. But the front edge, where new information begins, still respects the universal limit. The apparent acceleration arises from interference reshaping the pulse, not from any signal overtaking light. Experiments have produced situations where the peak of a pulse leaves a medium before the full pulse even enters, a striking optical illusion born from overlapping waves. Detailed analysis shows that energy and causality remain intact. The system rearranges existing components rather than creating forward transport of new content. Such studies are valuable because they teach where intuition breaks down. Velocity in a wave medium has many definitions: phase, group, energy, signal, and only one governs causality. Each demonstration of superluminal group speed strengthens, rather than weakens, our confidence in the boundary that light sets for communication. 59. Phase velocity can be faster than light without breaking causality. The phase of a wave, the points where its oscillations reach crests and troughs, can move faster than light depending on the medium's properties. This phase velocity does not represent transport of energy or information. It is simply the rate at which a constant phase propagates. In water waves and electromagnetic waves alike, the phase can outpace the group or even become infinite near resonance conditions. Relativity remains untouched because messages ride on modulation, the envelope or front of the wave, not on the phase itself. Engineers exploit this difference when designing waveguides and antennas, ensuring that the pattern's apparent speed does not confuse with signal propagation. Recognizing the distinction helps interpret data from plasma physics and fiber optics where measured velocities can seem paradoxical. Nature allows appearances of superluminal motion as long as nothing useful rides on them. The boundary between physical and illusory speed is one of the most subtle achievements of modern physics. 60. A prism delays colors by different amounts because of atomic resonances. When white light enters a prism, each wavelength encounters atoms that respond differently, slightly changing the speed and direction of the wave. Shorter wavelengths slow and bend more, spreading the beam into a spectrum. The amount of dispersion depends on how close each wavelength is to the material's electronic resonances, where atoms absorb and re-emit energy. The result turns the invisible structure of matter into a visible rainbow. Each colour's path length differs by fractions of micrometers inside the glass, and the cumulative delay at the exit face produces the familiar angular separation. Measuring that separation reveals the refractive index as a function of wavelength, a fingerprint of the material's internal energies. Dispersion is both an aesthetic and technological foundation. Spectrographs in astronomy dissect starlight to read chemical compositions, while optical fibers compensate dispersion to keep digital pulses sharp. In both cases, the constant C in vacuum anchors the reference, and every deviation in matter becomes an index against that ultimate speed. 61. The rainbow tells a story about light speed inside raindrops. A rainbow forms when sunlight enters spherical drops of water, refracts, reflects once inside, and then exits toward the observer. Each colour takes a slightly different path because light travels at different speeds in water depending on wavelength. This dispersion splits the sunlight into a band of colours arranged by angle, red on the outside and violet on the inside. The sharp boundary of the bow marks the direction where light from many drops reinforces itself most strongly. The phenomenon is an exercise in geometry and timing. Every photon that joins the bow has bounced within a raindrop at a particular angle, delayed by the slower speed of light in water. The vividness of the arc depends on how many drops contribute at those angles, and on how the human eye perceives overlapping colours. Double rainbows appear when light reflects twice inside the drops, reversing the colour order and dimming the secondary band. Rainbows demonstrate that the beauty of colour is a map of physics. The difference between air and water speeds transforms white light into a spectrum and the droplets into tiny prisms. When the storm passes and the sun returns, the sky itself acts as an optical instrument, revealing that nature's art is drawn by the constant interplay between light's speed and the matter it meets. 62. Slow glass is a myth, yet dispersion is real. In science fiction tales, slow glass holds images for years before releasing them, storing light as though it was syrup. Real materials cannot delay photons by such vast amounts without absorbing or transforming them. But the metaphor springs from genuine physics. In transparent substances, light already travels slower than in vacuum, and the exact amount depends on how the atoms and electrons within the medium react to oscillating electric fields. Dispersion describes that dependence. Different frequencies interact differently, causing red and blue to refract by distinct angles. While the idea of a pane of glass preserving yesterday's sunlight remains fantasy, laboratory slow light experiments in cold gases have achieved extreme but temporary delays through quantum effects. Even there, information never outruns the rules set by C. The apparent halt is an exchange of energy between light and atoms, not true storage of a travelling beam. The persistence of the myth points to our fascination with controlling time. We long to trap light, to replay the past. Physics reminds us that the vacuum speed is not negotiable, yet within that limit we can choreograph dazzling tricks of delay and release. The dream of slow glass endures as poetic shorthand for the real art of taming photons. 63. The fastest camera frames the birth of a light pulse in flight. Recent advances in streak and compressed ultrafast photography have captured light itself as it moves through transparent media. By firing laser pulses and using sensors that record at trillions of frames per second, researchers reconstruct how a pulse enters a bottle, reflects from surfaces, and exits. Each frame is separated by less than a trillionth of a second, short enough to track light over millimeters. These images are not filmed directly in real time. They are reconstructed from repeated measurements of synchronized events. Still, the result allows humans to visualize what was once beyond imagination, a beam creeping through space as if slowed by divine remote control. The apparent crawl is achieved by computational sequencing, not by altering the true speed. The ability to capture light in motion offers practical tools. Scientists study how photons scatter in fog, tissues or fibers, improving medical imaging and autonomous vision. The same techniques help art conservators look beneath paint layers without damage. The ultimate message remains humbling. Even when technology makes light appear to move like a snail, its real velocity never changes. It is our patience and algorithms that bridge the gap. 64. A mirror in motion changes the color of the reflected light. When a mirror moves toward an incoming beam, the reflected light is blue shifted. When it moves away, it is red shifted. The change in frequency is twice what it would be for a simple source moving relative to the observer, because the mirror encounters the incoming wavefronts faster and then launches them closer together. This Doppler effect for reflection proves that frequency, wavelength, and energy are all tied to relative motion. At everyday speeds, the shift is minuscule, but with mirrors mounted on high-velocity spacecraft or vibrating systems, the effect can be measured precisely. It enables devices such as laser interferometers to detect motion at the scale of nanometers by watching color or phase drift. Each oscillation of the mirror imprints its rhythm onto the returning light. The concept also connects to astrophysics. The surfaces of stars act like countless moving mirrors, scattering light whose frequencies encode turbulence, rotation, and pulsation. Every blue or red tilt in a spectral line tells of motion. The reflection Doppler shift is nature's unspoken language for revealing dynamics without touching the system. 65. Nothing can catch up to a light pulse to ride beside it. A photon always moves at the vacuum speed of light relative to any observer, leaving no frame of reference in which it stands still. No object with mass can accelerate enough to travel alongside, because the equations of relativity forbid a transition from slower to equal speed. For a material observer, attempting to match pace would require infinite energy. The notion of riding with light collapses because time itself halts in that direction. This limit shapes the geometry of space-time. Light defines the boundary between possible and impossible motion, the edges of light cones that mark causal structure. Everything that happens must occur within those cones, else it would need faster-than-light connection. The framework keeps the universe logically consistent, ensuring that sequences of cause and effect do not invert. Even thought experiments that imagine surfing on light waves reveal contradictions. Frequencies would freeze, time would cease, and distances would blur into undefined states. The very concept of observation depends on being slower than light. Reality builds its stage around that fact, reserving perfect speed for messengers that have no mass, no rest, and no rival. 66. The Doppler shift of light writes the speed of galaxies on the sky. Every galaxy that recedes from us stretches the wavelengths of its emitted light, shifting spectral lines toward red. The amount of shift tells astronomers the galaxy's velocity relative to Earth, allowing the first map of cosmic expansion. Those that move toward us show the opposite, blue shifts, though they are rare beyond our local group. Each shift is a direct measure of motion written in color rather than ink. Spectrographs split starlight into rainbows finely enough to resolve even tiny displacements. The redshift of distant galaxies correlates with distance, a relation that became the basis for Hubble's law and for the discovery that the universe is expanding. Later refinements showed that space itself stretches, carrying galaxies apart while light elongates in sympathy. The Doppler principle, once a tool for radar guns and weather forecasts, becomes a ruler for cosmic fate. The deeper the red, the older and farther the source. By measuring these hues, humanity reads the narrative of expansion directly from the palette of the sky, proof that colour is the handwriting of motion. 67. The meter once shrank and grew with temperature until light affected it. For more than a century, the world's standard of length was a platinum iridium bar kept near Paris. Despite meticulous care, temperature and handling changed its size by tiny amounts, causing global inconsistencies. The redefinition of the meter in terms of the vacuum speed of light and the second eliminated this fragility. Light's constancy replaced metal's instability. Now laboratories realize the meter by counting oscillations of stabilized lasers referenced to atomic transitions. A simple calculation of time multiplied by c yields length anywhere, unaffected by weather or age. The once sacred artifact became a museum piece, replaced by an equation valid in every lab, spacecraft, or mountain observatory. This transition symbolizes the maturation of measurement science, from reliance on material prototypes to reliance on fundamental constants. The meter is no longer an object to be guarded, but a principle to be applied. The revolution turned light itself into humanity's most trustworthy ruler. 68. A star behind a star can be copied into many images by gravity. When light from a distant galaxy passes near a massive object such as another galaxy or cluster, gravity bends its path into multiple routes that converge at the observer. The result is gravitational lensing, where the background source appears duplicated, stretched, or ring-shaped around the lens. Each image represents light that left the source at the same time, but travelled through different curved corridors of space-time. These natural lenses magnify faint sources and let astronomers probe the distribution of dark matter that supplies the necessary gravity. Time delays between the images reveal distances and expansion rates, turning the universe into its own telescope. No glass or mirror could achieve such power. Lensing dramatizes how mass sculpts geometry and how light obeys it. The multiple portraits of one object are snapshots of the same moment seen through distinct histories. The spectacle reminds us that in the cosmos, vision is never straightforward. Every gleam may have journeyed along several invisible detours before reaching the eye. 69, a ring of light can weigh a tiny amount through its energy. Energy and mass are equivalent through Einstein's formula, and because light carries energy, it also contributes a minuscule gravitational pull. A ring cavity filled with circulating laser light weighs ever so slightly more than when the light is off. The difference is absurdly small but real. Energy curves spacetime regardless of form. In theory, enough trapped radiation could mimic a kind of photon pressure vessel, though practical limits make such devices beyond reach. Still, the concept influences cosmology, where radiation dominated the early universe and gravity of light itself shaped expansion. Even today, the cosmic microwave background adds a faint contribution to the overall mass-energy balance. This subtle equivalence teaches humility about separations between matter and energy. Whether frozen into particles or racing as waves, all energy contributes to the curvature of the universe. Even a humble laser ring whispers with the weight of light. 70. The shortest possible signal is limited by quantum time and light. Quantum mechanics and relativity together set a lower bound on how quickly any event can be localized. The Planck time, about 10 to the minus 43 seconds, combines the gravitational constant, Planck's constant, and the vacuum speed of light. Below this scale, current theories lose coherence. Concepts like before and after cease to have meaning. A pulse shorter than this would require energies so immense that it would collapse into a black hole. This boundary is not a technological inconvenience, but a conceptual horizon. It marks where spacetime's smooth fabric may give way to quantum granularity. Physicists speculate that beyond it lies a realm of foamy geometry where light speed itself might emerge as an averaged property. In practice, the limit ensures stability. No signal can have infinite sharpness or carry infinite information density. The marriage of quantum uncertainty and light's constancy prevents nature from self-destruction through over-precision. The universe thus maintains order by forbidding both infinite speed and infinitesimal duration, a balance etched into existence. 71. The twin story is real for precise clocks on airplanes. When synchronized atomic clocks are flown around Earth on jets, the one that travels returns slightly behind its stationary twin. Both special and general relativity contribute to this effect. Motion slows the moving clock's rhythm while weaker gravity at altitude speeds it up. The combination matches predictions to remarkable precision, confirming that time is elastic, woven into motion and gravity together. The first such experiments in the 1970s used cesium clocks bulky enough to fill luggage compartments, yet even with their limitations, the difference was measurable in nanoseconds. Modern optical clocks, millions of times more precise, can detect time dilation over a change of altitude of just a few centimeters. Clocks become instruments that map spacetime's curvature by simply existing at different heights and speeds. These findings are no longer confined to laboratories. Every satellite, from navigation constellations to weather observers, incorporates these corrections into its timing algorithms. Airborne and orbital clocks prove daily that the twin paradox is not a story. It is the everyday arithmetic of the moving world, quiet symphony where every tick reveals a new layer of reality. 72. Why a perfect mirror cannot reflect every photon forever. Even the most flawless mirror loses a minute fraction of light with each reflection. Photons can be absorbed, scattered by microscopic imperfections, or converted into heat through interaction with electrons. Quantum theory ensures that no surface can have an infinite lifetime for photons, because boundary atoms always possess ways to steal a tiny portion of energy. Over countless bounces in optical cavities, these losses accumulate. Engineers characterize them as mirror finesse, a measure of how many reflections occur before a photon is lost. Mirrors with billions of reflections exist, yet eventually the stored light decays, leaking out or heating the substrate. Thermodynamics demands that isolation is never perfect. Entropy always claims its fee. In cosmic terms, even the universe is not an eternal mirror. Dust, gas, and plasma scatter photons endlessly, turning bright bursts into diffuse glows. Light's journey is long, but not infinite. The concept of a perfect reflection, while elegant in mathematics, meets the graininess of matter in practice, a reminder that purity in physics is always an approximation granted by patience, not by permanence. 73. Interferometers can feel continental drift with light. An interferometer splits a beam of light into two paths and recombines them to measure differences smaller than a wavelength. When the Earth's crust shifts by millimeters or the ground swells from tides, the interference fringes slide, revealing the motion. Geophysicists install laser interferometers in tunnels and observatories to detect continental drift, ground vibrations, and even subtle changes in air density. This sensitivity arises because light's wavelength is so short and its frequency so stable. A shift of half a micron in path length can flip bright to dark at the detector. Over long baselines, such tiny displacements correspond to tectonic motion. Instruments designed for gravitational waves can also hit earthquakes, storms, and moving glaciers through these optical whispers. By turning light into a ruler of impossible precision, humanity listens to the planet's slow breathing. Each phase change in the interference pattern is a syllable in Earth's quiet conversation. The same technique that measures galaxies' distances measures the tremor of soil beneath our feet, uniting cosmic and terrestrial motion in one language of time and phase. 74. A cavity filled with light becomes heavier than the same cavity dark. When photons bounce between mirrored walls, their energy contributes to the total mass of the system, according to the equivalence of energy and mass. Though infinitesimal, the difference can, in principle, be weighed. Energy has gravity. Experiments designed to detect this effect use precision balances and resonators to compare cavities with and without stored light, testing Einstein's prediction at the new levels. The result reveals that energy, regardless of form, bends spacetime just as matter does. Even trapped radiation, massless individually, collectively exerts weight. The heavier cavity illustrates that mass is not an inherent substance but a measure of total energy content. This insight links the smallest photon to the largest cosmos. In the early universe, radiation dominated matter, shaping expansion through its gravity. The same rule governing a tiny optical resonator governed the birth of galaxies. The weight of light reminds physicists that energy and geometry are never strangers. They are the same entity viewed through different eyes. 75. Light digs tunnels in air and makes filaments. When extremely intense laser pulses travel through air, their electric fields can ionize molecules and create plasma channels that act like self-made waveguides. The beam balances two effects: the natural tendency to spread by diffraction and the focusing pull from the plasma's refractive index. The result is a filament, a narrow thread of light that can stretch over long distances without diverging. These filaments behave almost like lightning made of photons. They can trigger electric discharges, mark paths for communication through turbulent air, or study how storms form. Each filament arises from a dance between light's pressure and the medium's response, carving temporary tunnels of transparency as it advances. The phenomenon reveals how nonlinear optics allows light to sculpt its own environment. At extreme intensities, the medium no longer passively hosts the beam. It fights back and reshapes it. Filamentation is light writing with itself, a vivid example of how the same constant speed and frequency interplay that make rainbows can, at higher energy, forge structures in thin air. 76. A moving medium can drag light and change its measured speed. In 1851, Hippolyte Fizeau discovered that when light travels through flowing water, its speed relative to an observer depends on both the water's motion and the refractive index. The effect, partial dragging of the light, proved that the medium influences propagation, but does not simply carry light along like a current. The measured shift supported the emerging idea that light's behavior is governed by relativity, not by a stationary ether. The dragging coefficient matched predictions that later found a natural explanation in Einstein's framework. The combination of velocities follows the rules of special relativity, preserving the invariant speed of light in vacuum. The experiment became one of the stepping stones from classical optics to modern spacetime. Today, the Fizeau effect lives on in fiber optic gyroscopes and precision sensors where moving media, rotating frames, or atmospheric flows can subtly alter phase. Each measurement reminds us that motion and light interact in precise proportions dictated by geometry. Even before relativity was named, light had already been whispering its secret. 77. The first astronomical speed of light came from a moon and a shadow. In 1676, Ole Rømer noticed that the eclipses of Jupiter's moon Io occurred earlier or later depending on Earth's position relative to Jupiter. As Earth moved toward the planet, the events arrived ahead of schedule. As it moved away, they lagged. Rømer concluded that light took time to cross the changing distance between worlds, about 22 minutes across the diameter of Earth's orbit. It was the first proof that light's speed was finite. The deduction required no clocks faster than celestial mechanics. By comparing predicted and observed timings, Rømer turned the solar system into a vast laboratory. Later refinements yielded more accurate values, but the principle was established. Light, though swift, needs time. This insight broke a philosophical barrier. Until then, many assumed light acted instantaneously, a divine or instantaneous influence. Rømer's discovery gave the cosmos a measurable tempo. Every beam since then has been seen as a traveller, not a miracle. Its velocity finite yet vast enough to link planets, stars, and thought itself. 78. The vacuum speed of light ties together electric and magnetic constants. The value of c is not arbitrary. It arises from the relationship between the electric constant, permittivity of free space, and the magnetic constant, permeability of free space. When James Clerk Maxwell combined the laws of electricity and magnetism, he found that disturbances in the electromagnetic field propagate at a speed equal to 1 divided by the square root of their product. The number matched known estimates of light's velocity, revealing that light is an electromagnetic wave. This unification transformed science. The equations not only described optics but predicted radio waves decades before they were discovered. The constants that seemed abstract now defined the speed of the universe's messenger. Every wireless signal, every photon, every colour of the rainbow obeys this same heritage. The link between field and speed means that c is not imposed by decree, but born from the fabric of electromagnetism itself. Light travels as fast as space allows because space is built from the fields that define that very speed. 79. Light defines the difference between space and time in equations. In relativity, the interval that separates events combines distance and duration in a single formula, time multiplied by the vacuum speed of light squared minus spatial distance squared. The boundary between positive and negative intervals marks the distinction between time-like and space-like separations, between what can influence what and what cannot. Light-like intervals sit exactly on that border. This mathematical structure transforms geometry into physics. The metric of space-time is scaled by c, giving time the same units as space and knitting them into one continuum. Without light's fixed speed, there would be no natural way to convert seconds into meters or to describe motion as a rotation in space-time. The appearance of c in every relativistic equation is thus not decorative but structural. It is the translation constant between two ways of counting reality. When we write E equals mc squared or compute how clocks tick in motion, we are using light as the interpreter between the languages of distance and duration. AT, a beam splitter, decides paths without deciding the destination. In an interferometer, a beam splitter sends part of an incoming wave down one route and part down another. Each fragment retains coherence with the other, so when recombined they interfere, producing fringes of brightness and darkness. Until measurement occurs, the photon's probability amplitude spans both paths simultaneously, carrying information about the length difference between them. The device embodies quantum duality in pure form. Adjust one mirror by a fraction of a wavelength and the interference pattern shifts, revealing the sensitivity of phase to path length. Yet when detectors are placed to determine which path the photon took, the interference disappears. The act of asking breaks the superposition that produced the fringes. Beam splitters underpin technologies from gravitational wave detectors to quantum computers. They are the simplest gates of light logic, balancing indeterminacy and control. Each time a photon meets that half-silvered surface, nature rolls its silent dice, but always in accord with the rules written by the unyielding speed of light. 81. The angle of starlight arrival depends on how fast the telescope moves. When a telescope on Earth captures light from a distant star, the planet's orbital motion slightly tilts the apparent direction of the incoming rays. This tilt, known as stellar aberration, is tiny, only about 20 arcseconds, but measurable. It arises because during the time light travels through the telescope tube, the instrument itself moves keepways along with Earth, so the telescope must be pointed a little ahead of the true stellar position to catch the beam. This discovery in the 18th century confirmed that light does not arrive instantaneously and that Earth is indeed in motion around the Sun. The magnitude of the tilt directly encodes the ratio between Earth's orbital speed and the vacuum speed of light, offering one of the first terrestrial ways to measure that cosmic constant. It turned the sky into a speedometer for our planet. Today, the same correction remains vital for precise astrometry. Modern space telescopes orbiting Earth or the Sun adjust their pointing by calculating aberration from their velocity vectors. Every accurate star catalogue hides behind it an intricate ballet of light speed corrections, proof that even the simplest starlight carries the whisper of planetary motion. 82. Light from the early universe is stretched into microwaves by expansion. The cosmic microwave background we see today began as blazing radiation when the universe was about 380,000 years old. At that time, matter and light decoupled, letting photons travel freely for the first time. As space expanded over billions of years, those photons stretched to longer wavelengths, cooling from visible and infrared down to millimeter microwaves. The same waves that once lit a fireball now form a faint afterglow barely above absolute zero. This stretching is not a slowing down of photons. Each one still moves at the vacuum speed of light. Rather, the expansion of space itself elongates their wavelengths, reducing energy while preserving speed. The redshift thus encodes the history of cosmic growth directly into the frequency of light. By mapping slight temperature variations in this background, cosmologists infer the age, composition, and curvature of the cosmos. The relic radiation acts as both fossil and ruler. Light's constancy turns the universe into a readable chronicle where distance, time, and expansion all share one underlying beat. 83. A photon can be delayed by crystals that act like tiny mazes. In birefringent materials, light splits into two beams with different polarizations that travel at distinct speeds. Each path threads a separate lattice within the crystal, so the exit beams are delayed relative to each other by picoseconds or less. The effect allows manipulation of phase, enabling waveplates, polarizers, and timing controls for optical circuits. Inside the crystal, the atomic arrangement breaks symmetry, making one direction easier for the electric field of the wave to vibrate than another. The mismatch alters effective refractive indices and gives rise to phenomena such as double refraction, where a single image viewed through the crystal appears duplicated. These internal mazes of geometry turn rigid matter into a playground for photon choreography. Engineers exploit these delays to synchronize laser pulses, store quantum information briefly, or measure polarization with astonishing precision. Each photon's journey through the crystal is a miniature obstacle course, where direction and polarization decide the timing. Even at its smallest scales, the world uses light's constancy to measure its own asymmetries. 84. The fastest messenger in biology is still slower than an optical pulse. Nerve impulses in humans travel up to about 100 meters per second, quick by cellular standards, but minuscule compared to light. Even the fastest electrical signals in myelinated neurons crawl at a fraction of 1/1,000,000th of c. Communication within the body, though governed by electrochemical processes, is glacial beside the pace of photons that can circle Earth 7 times in a single second. This disparity defines biological limits. Reaction times, thought speeds, and sensory coordination are bound by these neural velocities. If our brains operated anywhere near light speed, perception itself would fracture. Simultaneity would vanish between senses. Evolution found a balance between speed and stability, letting slow chemical pulses sustain coherent awareness. Comparing biology to optics reveals perspective. What feels instantaneous in life is leisurely on the cosmic scale. Every movement, every reflex, is a slow dance inside a world ruled by a messenger infinitely faster, reminding us that perception measures time not by C, but by chemistry. 85. A femtosecond is long compared with the time a photon crosses a hair. A femtosecond, 1/quadrillionth of a second, is the timescale at which molecules vibrate and see chemical bonds break. Yet even in that blinkless instant, a photon travelling at light speed covers about 300 nanometers, nearly the width of a human hair divided by 200. Light's swiftness turns unimaginably small durations into meaningful distances. Ultrafast lasers use bursts lasting only a few femtoseconds to probe molecular dynamics. In that realm, reactions can be frozen frame by frame, allowing scientists to see electrons migrate and bonds rearrange. These snapshots form the foundation of femtochemistry, a field born from humanity's ability to control time itself through light. At such scales, causality remains intact but perception strains. For a photon, even a femtosecond is an eternity in its unmeasured proper time of zero. The juxtaposition between human control and cosmic constancy defines the art of ultrafast science, slowing the fastest thing in the universe just enough to watch it move. 86. The sharpness of an image is limited by the wavelength of light. No optical system can resolve details smaller than roughly half the wavelength of the light it uses. This diffraction limit arises because waves spread when passing through apertures, smearing information beyond a certain threshold. Microscopes working in visible light thus cannot see objects smaller than about 200 nanometers without special techniques. To break this barrier, scientists employ electron microscopes, which use much shorter de Broglie wavelengths, or exploit fluorescence methods that reconstruct images from many exposures of single molecules. Yet the fundamental principle remains: resolution depends on wavelength, and wavelength links directly to the speed of light and frequency through c equals lambda nu. The diffraction limit is both a constraint and a teacher. It forces ingenuity, inspiring super-resolution imaging, and quantum optics that dance at the edge of what waves permit. In every lens and camera, the crispness of reality is drawn not by craftsmanship alone, but by the unyielding relationship between light's speed, frequency, and geometry. 87. A perfect cloaking device is blocked by the rules of light. Science fiction dreams of invisibility often rely on bending light perfectly around an object so that it emerges undisturbed on the other side. Metamaterials can guide certain wavelengths and controlled paths, creating limited cloaking for narrow bands or specific directions. Yet a universal cloak for all colours and angles defies physics because it would require light to travel different distances at identical times, breaking the constraints of the vacuum speed of light. Even partial cloaks reveal the challenge. To hide an object completely, the light must accelerate and decelerate flawlessly, matching phases without distortion or absorption. Such manipulation would demand materials with properties that invert standard refractive behaviour across all frequencies, something no known matter can sustain. The pursuit, however, is scientifically fruitful. Cloaking research has led to improved lenses, adaptive optics, and materials that steer electromagnetic waves with precision. The impossibility of perfection fuels innovation, teaching that boundaries, not loopholes, are what drive creativity. Light cannot be fooled entirely, but it can be persuaded to perform remarkable tricks within its laws. 88. A negative refractive index bends light the other way. Ordinary materials bend light toward the normal when entering from air, but engineered metamaterials with negative refractive indices reverse this behavior. In such media, the direction of energy flow and the wave's phase are opposite. A beam entering them refracts on the same side of the normal instead of the opposite, producing counterintuitive focusing and reverse Doppler effects. These materials achieve their properties through microscopic structures smaller than the wavelength of light, not through chemistry. The geometry of these structures creates an effective response that flips the signs of electric and magnetic parameters. Though difficult to make for visible wavelengths, they have been demonstrated in microwaves and near-infrared regimes. Negative refraction opens the door to super lenses that beat traditional resolution limits, and to compact antennas and sensors. It reminds us that light's behavior depends not only on fundamental constants but on how we structure matter. Even while obeying C, light can be coaxed into seemingly impossible maneuvers by reshaping the playground it crosses. 89. A mirror that moves near light speed brightens the light it reflects. When a mirror races toward incoming radiation at relativistic velocity, the reflected photons gain energy. Their wavelengths compress, frequencies rise, and the beam becomes brighter and bluer. The process multiplies the photon energy by factors depending on the mirror's speed, turning ordinary reflections into bursts of high-energy radiation. Such moving mirrors are not built of metal, but of plasma fronts in laser experiments. By firing intense pulses into gases, physicists create waves of electrons that act as temporary reflective surfaces racing close to C. The reflected light emerges as attosecond flashes in X-ray frequencies, tools for probing atomic structure. This effect transforms the Doppler principle into an engine of creation, demonstrating how motion itself can forge new light. Even as photons respect the universal limit, matter in motion near that limit can channel their energy upward, bridging laboratory scales and cosmic phenomena like jets from black holes, where natural moving mirrors blaze across the universe. 90. A starquake can ring spacetime and light hears the bell. When neutron stars crack under their own stress, the sudden rearrangement releases both gravitational waves and bursts of light. The crust shatters, magnetic fields realign, and the entire star vibrates like a struck bell. Light emerging from these events carries oscillations matching those gravitational tones, proving that even the densest matter and radiation communicate through the same geometry. Space-time itself acts as the medium of sound, and light is its witness. As ripples pass through the cosmos, they stretch and squeeze the distance light must cross, slightly modulating its arrival. Sensitive detectors reading pulses from millisecond pulsars can detect these tiny timing shifts, turning distant stars into galactic seismographs. Starquakes remind us that in the universe, light is never deaf. Even when born from violence, it faithfully records the rhythm of events billions of years away. Each photon arriving at Earth carries not just brightness, but a vibration, a message about how the cosmos itself trembles and recovers. 91. The color that never existed until lasers carved it from frequency space. Before the invention of lasers, light was confined to the discrete wavelengths produced by natural sources, incandescent filaments, chemical reactions, or stars. Lasers introduced a new kind of precision, allowing humans to generate light at frequencies that never occurred naturally by stimulating coherent emission inside tailored materials. The result was not merely brightness, but control, an ability to sculpt photons at will. By adjusting atomic energy levels, optical cavities and pump mechanisms, scientists now create laser light in hues far beyond the visible spectrum, ultraviolet, infrared, even X-ray. Each color corresponds to a frequency chosen with mathematical rigor, turning color from an accident of chemistry into an engineered coordinate on the electromagnetic map. These new colors unlocked technologies that define modern life: fiber optic communication, laser surgery, holography, and quantum computing. A frequency once absent from nature now carries our voices across continents. The universe gave us a spectrum, the laser gave us the keys to fill its silent gaps. 92. Light can cool atoms by making them chase a moving color. When laser light is tuned slightly below an atomic resonance, atoms moving toward the beam see the light Doppler shifted closer to their natural frequency and absorb it. Each absorption and re-emission slows the atoms, reducing their kinetic energy. The process, known as laser cooling, can bring gases down to microkelvin temperatures, where motion nearly stops and quantum effects dominate. The cooling works because the momentum of each photon opposes the atom's motion. Millions of scattered photons gradually remove velocity in all directions. Atoms can then be trapped in magnetic or optical fields to create Bose-Einstein condensates, macroscopic quantum states where matter behaves as a single wave. This control over motion redefined experimental physics. Once unreachable realms of temperature became accessible, allowing clocks of unprecedented accuracy and studies of quantum phenomena that underpin modern technology. The method's elegance lies in its obedience to the rules of light speed and momentum, slowing matter by using the universe's fastest messenger. 93. The universe keeps a ledger with light cones. Every event in space-time defines a light cone, an expanding sphere marking where its influence can reach at the vacuum speed of light and where it cannot. The future cone contains all possible consequences. The past cone, all possible causes. Events outside both are forever separate, unable to communicate without violating causality. The cosmos thus maintains order not through fences, but through geometry. These cones overlap and intersect, linking histories into a web of connected possibilities. Where cones meet, communication and interaction become possible. Where they miss, silence prevails. Relativity draws the entire universe as a network of such intersections, a cosmic bookkeeping system that keeps track of what can know what. This structure ensures consistency of narratives across observers. No matter how fast one moves, cause always precedes effect within each cone. The speed of light is not just a limit, it is the cosmic auditor, ensuring every transaction of energy or information balances within its proper domain of time. 94. The Planck length is where space may stop being smooth. At about 1.6 times 10 to the negative 35th meters lies the Planck length, the scale at which quantum fluctuations of space-time itself become significant. Below this, our familiar notions of geometry may dissolve into probabilistic foam. The constants that define it, Planck's constant, the gravitational constant, and the vacuum speed of light, combine to set a threshold where gravity and quantum mechanics must unify. Physicists suspect that at this length distances cannot be meaningfully subdivided. Attempting to probe smaller regions would require energies so vast they would form a black hole, hiding the very information sought. Space could be granular, woven from discrete quanta rather than continuous threads. No current experiment can reach this realm, but its existence serves as a compass for theory. String theory, loop quantum gravity, and holographic models all aim to describe how space-time behaves there. The Planck length is the whisper at the bottom of physics, the point where light, gravity, and quantum uncertainty shake hands and blur identity. 95. A photon clock defines time with the tick of a wave. Imagine two mirrors facing each other with a single photon bouncing back and forth. Each round trip marks a tick, its duration determined by the distance between mirrors divided by the vacuum speed of light. Such a photon clock is the conceptual heart of relativity. Time is what light measures when confined by geometry. In motion, the photon's path lengthens, forcing the ticks to slow relative to a stationary observer. This thought experiment, simple yet profound, led to time dilation and the realization that all clocks, mechanical, biological, or atomic, must follow the same rule if physics is to remain consistent. Today, lasers and cavities embody this principle in real instruments. The oscillations of light serve as the most stable rhythms known, defining the second with precision unimagined a century ago. Each pulse of a photon clock is a heartbeat of the cosmos, set to the cadence that nature will not allow to change. 96. Information cannot flow faster than light even in quantum tricks. No matter how exotic the quantum phenomenon, tunneling, entanglement, or wave function collapse, experiments confirm that no usable information travels faster than the vacuum speed of light. The universe forbids shortcuts. Even processes that seem instantaneous from one viewpoint rely on classical channels to share results. This rule safeguards causality. Without it, one observer could send messages into another's past, unraveling the logical sequence of cause and effect. Quantum teleportation, for example, transmits a state only after conventional communication, bound by a light speed, links sender and receiver. The temptation to imagine loopholes persists, but every verified test reaffirms the limit's resilience. Nature's code is unbreakable not by decree but by self-consistency. The universe is a perfect cryptographer. Its encryption key is C, and every quantum experiment signs its data with that constant. 97. The edge of a shadow can creep faster than light and carry no news. When a distant object casts a shadow on a curved surface, the point where darkness first appears can sweep across that surface faster than the vacuum speed of light. This happens because the geometry of projection amplifies small motions of the blocking object into vast apparent speeds at great distances. The moving edge is not a physical entity. It has no mass, energy, or signal to convey. Such effects occur in solar eclipses, where the lunar shadow sweeps Earth faster than any spacecraft could travel. Yet no observer experiences superluminal contact. Each location darkens only when local light is blocked. The sweeping edge is a pattern, not a messenger. The lesson is subtle. Speed applies only to things that carry information or energy. Shadows, laser spots, and interference fringes can break the limit in appearance, but never in substance. Light's speed remains untouched, even as its absence seems to outrun it. 98. A single atom can hold and release a photon like a memory. Quantum optics allows individual atoms to absorb and later emit single photons, preserving their phase and polarization. These systems act as quantum memories, storing the information carried by light for controlled release. By tuning magnetic fields and laser pulses, researchers can decide when the atom should let go, effectively freezing and reviving a photon's identity. The interaction hinges on resonance. The atomic energy levels must match the photon's frequency precisely. When they do, the exchange becomes coherent, maintaining quantum superpositions and enabling entanglement between light and matter. Such precision turns a single atom into a switch that bridges communication between photons and stationary qubits. This mastery of light-matter dialogue is foundational for quantum networks. By passing photons between atomic memories, information can be transmitted securely over long distances. In each exchange, the photon respects the cosmic limit. It pauses within the atom, never exceeding c, proving that even stored light remains a loyal subject of its constant. 99. A mirror farther than a light-year returns an answer after human lifetimes. Place a perfect mirror 1 light-year away, send a pulse, and the reflection will return 2 years later. The simplicity hides profundity. Communication over cosmic scales is limited not by technology but by geometry. Each additional light-year adds another year of waiting each way, setting an unbreakable cadence to interstellar conversation. This delay defines the patience required for exploration. Messages to distant probes, stars, or hypothetical civilizations unfold over centuries or millennia. The universe's vastness is measured not only in distance but in time, multiplied by light's constant. Every inquiry to the cosmos is a question whose answer is guaranteed to be ancient when it arrives. Yet this slowness carries poetry. The reflection that returns is the echo of a younger Earth, a ghost image of who we were when the beam left. Light speed enforces humility. It ensures that looking outward is also looking backward into the history of our own signal. 100. The speed of light is the hinge that makes the universe logical. Every theory, from relativity to quantum electrodynamics, rests on one unwavering pillar, that the vacuum speed of light is constant for all observers. This single rule binds space to time, energy to mass, cause to effect. It turns the chaos of motion into order, giving every event a predictable relationship to every other. Without it, geometry, communication, and even identity would crumble. The constancy of c is more than a number. It is the grammar of reality. It defines the maximum pace of influence, the fabric of simultaneity, the scale of energy itself. From the smallest photon's journey to the expansion of galaxies, all phenomena respect its authority. When we measure distance, when we synchronize clocks, when we send a thought as radio waves through the night, we are invoking that universal rhythm. The universe remains coherent because light never changes its mind. It is the silent hinge on which everything turns, the heartbeat of space-time itself. As the final notes of this journey fade, remember that every beam of light you have heard about tonight, every photon, every ripple, every glimmer, is still moving through the dark, steady and unwavering, tracing the same constant path that shapes the universe itself. The speed of light is more than motion. It is the heartbeat of existence, the quiet rhythm that keeps time for galaxies, atoms, and dreams alike. As you drift into sleep, imagine that rhythm surrounding you, endless, calm, eternal, carrying your thoughts outward through the cosmos, across the same boundless space that connects every star to every sleeping mind on Earth. Let that thought slow your breathing. You are part of that same cosmic light, still traveling, still shining. If you enjoyed this journey, don't forget to like the video, comment, and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be much stranger than we realize. Science is the most powerful way to understand this strangeness.